So good morning. I've got the inevitable job of giving the talk before lunch. So hopefully I'll keep your interest here. Anyway, so let me know if I need to increase the font size for anything. I've got some contact information there. I'm AJ Rader, Director of Data Science at DMC Insurance. And I'm going to talk a little bit about natural language processing. So DMC Insurance put up this picture of a truck because we insure trucks. We insure fleet trucks, usually 35, 40 plus units up to over hundreds of units in a fleet. So that's the type of insurance that we do. So I'm not going to talk to you about insurance. I'm not going to try to sell you insurance today. But we are hiring data scientists and data analysts. So if you're interested, you're looking, or you know somebody's looking, come see me afterwards and I'll talk to you more about that. As Calvin said, now for something completely different, natural language processing. So I'm doing this whole talk in a Jupyter notebook. I figured we're at a PyData conference. I went to my first PyData conference 5 years ago, and it really just sold me on using Python for everything all the time. And so back then, they weren't called Jupyter notebooks, they were called IPython notebooks, but the same sort of thing. And I got to meet a lot of those folks that do that sort of stuff, and it was a really exciting community. And I think one of the things I took away from that, I tried to ingest into this sort of talk, is to say, let's put this in a format where you can learn something from it, and that I can learn something from it, and that people can do that. So I put things up there. If you notice, I
Hello? Here, maybe just try this one for now. It's back on now.
Working? No. All right, we'll go this way. So I put my, yes, at the bottom there, it's on GitHub under my my account. So you can download this and deal with it offline. So anyway, like I said, if you've had too many donuts and the sugar crash is going to come soon, the TLD here is that NLP involves converting words into numbers and doing math on these numbers in order to identify the relationships between them. So we're going to take this library and convert it into bits, because that's what a computer reads. It doesn't read books, it reads numbers. So, like I said, why NLP, right? So this is a very broad domain, right? There's a lot of different things you can do with it. Everything from text classification to machine translation. So the Google translation of websites, or even in speech format. Language modeling, which I think is really cool, to be able to predict what the next word might be. Your search engine possibly might use that. Developing captions for pictures, summarizing blocks of text, speech recognition, answering questions by chatbots, all these sorts of things. So these are all applications of using NLP. And the point is that words have power, right? And so what do we do with that? How do we deal with that? I think this comment here that NLP, unlike so many things that we do in data science, the inputs for it are generally unstructured, or maybe it's semi-structured. You could argue about that, but it's different than a lot of approaches. So if you come from more of a statistical standpoint in data science, it's very natural to think about numbers and to think about regression and even logistic regression. You're still just doing transformations on that. With words, it's not quite the same thing, right? You've got to figure out how to take these words and convert them into vectors or into numbers so that you can do the math on them, because that's what we're going to do, because a computer does math really well. A computer doesn't read really well, but it does math really well. So some of the favorite, or go-to tools or approaches wouldn't work without some sort of pre-processing. So how have I used, why am I giving this talk? Maybe that's a better way of phrasing this, is that, so over the years, I've dabbled in NLP, text mining. I mean, I kind of use those two interchangeably because maybe the place to start is with text mining. And so I've done some things where at a previous job, I characterized articles written. And so doing that, trying to assign topics and determine what the voice of the writers were. And with that, identifying entities so that we could connect and recommend content based upon that. And then dealt with that to figure out seasonality. At a previous job for an insurance company, not the one I'm at now, we analyzed claims notes to identify common features in claims. And so we had this little, there's a screenshot of a thing that we put together in a hack day where we were looking at claims, and we saw that claims involving, you're not going to be able to read that, but there was a pipe burst, and that big peak was around the time of the polar vortex several years ago, if you remember. So, there were a lot more claims coming in that had things about pipe breaking and or internal water, right, was the phrase. And so we were like, oh, it correlated, So it was post-analysis, but it gives you a sense of like how things could happen, and it builds a way of going to this. So clearly doing all this stuff, right, sentiment analysis, just determining topics, doing machine translation, it's way too much for a full talk, to cover in a short talk. So we're just gonna start with a few things. So my goals for this morning, and we may or may not get through all of this, but we'll go where we get to, is to provide an overview of some concepts, terms, and methods, and then illustrates a few examples. And I can pause and see there was a question about what's the use case or business need of NLP in insurance business. So no, it's a great question. So I'll say a little bit about that. I would say, so the examples I'm going to present today, it's more of a tutorial, something that I could post on GitHub that anyone can look at. But this comment about what I did at a previous company it's looking at a lot of the claim stuff. So in that case, it's ironic. It may not be exactly natural language processing if you've ever looked at the notes that come through, because usually there's a lot of shorthand that goes into it because they're just quick jots, and they get put into a database because the databases were set up years and years ago, and so they have character width limits and things like that. So so doing things like that, but a lot of it from a business use case is one of the most or lowest hanging fruits is looking at the claims notes, and so I've been able to look at identifying which claims might participate in certain things, and then from that make a decision about how quickly we could turn around and settle that claim, right? So it helps the customer to get their money quicker if it's an easy processing thing. So so thanks for that question. All right, so let's do some terms, sorry, and then I'll get into some of the meat of the Python code. So let me mention these terms. So tokenization. Tokenization is just breaking the text into smaller pieces. Oh, I gotta make this bigger, right? You guys can't see that? Maybe. Can you guys read that now? Is it not zooming? Oh, there. All right. So stop words are non-important words, right? So these are typically things like the, and. There's more of it, but that's something else. And then Engrams, which I'm not going to go into too much, but these are groupings of adjacent words. So I'm going to work with just 1 grams, so they're single words, but you could think about bigrams, trigrams, so on and so forth. And it's an easy way to capture some of the co-localization of specific words. So if you think about it, instead of knowing that it's, a bag, you can say, well, it's a shopping bag. So using the context around it helps with that. Stemming and lemmatization are ways to collapse similar words. So for example, how to deal with plurals, how to deal with different tenses of verbs, and things like that. And so it's a method of trying to reduce the dimensionality. In some ways, those two things work against each other, the engrams versus the stemming, because engrams could increase the dimensionality because you consider every possible pairing, and then stemming and lemmatization help you reduce that dimensionality. Oop. So as you can see, this is all marked down because it's a notebook. Let's see, a few more terms. Part of speech tagging. So this is a way of identifying what, this is part of adding some of the structure back into the NLP or the language. So you add in whether it's a verb or a noun. So if you remember back in grade school, if you did this sentence diagramming, identifying all those sorts of things, we're using a computer to try to do that, and then that helps distinguish different uses of a particular word. So you could say the car is banks, right? Because it's going around a corner, or I'm going to the bank, which is a very different word, right? They're different words, and so to help distinguish those two words from one another, even though it's the same characters, right? You have to do that by part-of-speech tagging. And then named entity recognition, which I won't go into today, it's a different feature, right? But it's a way of saying these are our proper nouns, our people, our places, things, and those often carry a lot of weight because a lot of times, if you're looking at what is a document or a corpus of documents about, then you want to know the person, right, or the thing that they're talking about. And so NER works with that a lot. And I mentioned this word corpus, so that's just a set of documents. All right, let's start simply. I've done a lot of words. So we're gonna represent a set of documents by a vector space defined by, and so now I'm gonna try to minimize a little bit, sorry. Step it down one. So we set up these vectors, and they're going to be assumed to be orthogonal to one another. And this will give us the way to locate the document in the word space. So if we have n words, right, unique words, in our set of m documents, then our vector space will have a dimensionality of n. So in doing this, we're just going to ignore the context, right? So we're going to start simply. We're going to deal with unigrams or one-grams, and this is the so-called bag of words approach. So if you've heard of bag of words approach, that's what I'm doing here, because it's always good to start walking before you run. And if we can understand this, and hopefully by the end of this talk, I'll give you some examples of doing a little more complicated things. So let's start with a toy example. So let's do a simple example where there are only 3 words in our documents: airplane, boat, and car. And so every sentence or document is constructed only out of these words, right? So to convert these into an orthogonal basis set, we would explicitly define this as airplane is 100, boat is 010, and car is 001. And so when we put this in a vector space, we have an airplane axis, a boat axis, and a car axis. And so if we have a document over here, it's a linear combination of those 3 items, right? So if we put in a toy corpus, so these are nonsensical sentences, but they are sentences, right? Boat, airplane, airplane, boat, car. It's what our dictionary, our corpus is made out of as far as words. The next one is car, airplane, car, boat, car, airplane, and so on, right? So we have, I think I put 6 sentences in there. No, 7. The easiest way to do this is then to define the number of occurrences of each word as the value along the axis for that word, and then we represent them in this vector format. So boat, airplane, airplane, boat, car becomes 2, 2, 1, and so forth. So you get these different vector representations of all of these sentences, right? So doing this, we can then say, well, what do we want to do with this? And one of the starting points is to say, well, what's similar to each other, right? If we're going to try to characterize this corpus, one thing to try to say is like, well, is sentence A more similar to sentence B, or is it more similar to sentence C? Because that then tells us something about what those things are saying, and that's a starting point, right? Because then we can start to cluster things and go from there. So the easiest way to do that is to measure the similarity of these vectors. So the distance, which cosine similarity makes sense, and I'm going to rely heavily on some standard Python library. Scikit-learn's count vectorizer does that, so we import that. And so I'll do this one. This one won't take long at all to do. So we take that in. We create this count vectorizer. We fit our toy corpus that I loaded, and then we can output what the transformed is. So this actually took, I don't know if you noticed that. So I had here added my toy corpus as these sentences, right? And then just using the standard scikit-learn mechanism, we import them, the count vectorizer is the function, and then we fit the toy corpus to that, and then as we transform our toy corpus to an array, we get it in the vector form. So similar methodology is what scikit-learn uses for its methods. So to visualize that, I bring in a few helper functions here, and then I'm going to plot just in a 3D space because I just have three dimensions because of my airplane, boat, and car. So each of my sentences now are represented by a dot. And so you can see, well, these two are pretty close. These two are pretty close, but very far from this one. And I can actually then calculate my similarity matrix by doing a cosine similarity of those and do it as a heat map here. So the diagonal is, of course, self-similarity. So each row and column are a sentence. So we're saying this is self-similarity, but you see that, oh, these two, numbers 1 and 2 sentences are pretty similar to one another. And that heat map is just an easy way to visualize it, right? Sorry, I hit the wrong button. All right, so, and if we wanted to, we could actually, from our calculated similarity matrix, right, we can see that, oh, 2 and 3, right, so, oh yeah, those are low similarity ones, right, 2 and 3. Have low similarity, they have a similarity of 0.22, and if you look at the second element, sorry, these are in keeping with true computer science notation, these are 0 indexed, right? So we'll have that argument later if you want to have it. But so car, airplane, very dissimilar from this one because they're, they only match up on the airplane dimension, right? Versus comparing sentence 1 and 2, which have a similarity of 0.96, and those overlap much better. So, all right, you've now walked through, you've learned to walk, right? So baby steps, we're gonna go a little bit further now. So what are some possible problems with bag of words approach? Well, one, typically our sentence isn't just these vehicles, right? We have a lot of words that are very common, the, and, or, but don't really carry much information. And so these are typically referred to stop words. And we can just eliminate those. That'd be one way to do it. But then even within that, there's usually additional high-frequency words that don't contribute much discriminating information. Because what we want to do is if we want to compare things, we want to figure out how to discriminate among them. So. Oops, too far. So if we do that, for example, in an article written about March Madness, words like NCAA or basketball or college don't provide much additional information, and so we may not want to, keep counting those. And then when we use words as the atomic base or as the basis, right? They don't have any semantic relations. So again, this goes back to the notion of the sense of like, really, if a article is talking about a car or a truck, those things actually are more similar. So how do we figure out similarity in that way versus an article that's talking about babies and cats or something like that? So we need to figure out how to relate them in a better way, and that's part of that bag of words moniker that we don't really distinguish that. And then, of course, we don't have any syntax. We've thrown all that out. All we've done is just concatenated a bunch of strings of words. So let's just, as we start to walk a little further, let's take a more complicated example of the text of a book. So I'm going to use Project Gutenberg, which is an online library of free ebooks. A lot of classics are in there. And so I'm going to use that to download some texts and process them and then do comparison of that. So that way it'll give me some sense to understand the different pre-processing steps and packages. And hopefully by doing that, you'll see what some of these pre-processing steps need to happen. So I've written a couple helper functions, so that helps me download this. So as you can see, I chose several books, and I try to, I use encoding, and I strip out some lines, and I won't go into all the details of this function, but it's there. I created a class for some reason and put them into, but I can split the book into chapters because I thought maybe it makes a difference whether we do the whole thing or do it by chapters. But let's just take an example text, the classic Around the World in 80 Days by Jules Verne. So this is book 103 in their database, and so I can load that in. And so it loads it in and it splits it into chapters. So this has 37 chapters, and the entire book has 364,000 characters in it. So how do we deal with this? Well, one way is to tokenize it, right? Let's consider all the words in the book. Let's apply the approach we did with Bag of Words. So the methods to tokenize, remember, tokenize is just splitting it into words, right? Or Engrams if you want to do it that way too. So you could use an NLTK. Scikit-learn has a package. The standard library, you could do it. You could build your own using regex. There are times when that comes into play. The comment about using it on not natural language. So, for example, if you're doing Twitter stuff, sometimes you may need to build your own parsers to deal with some of the either slang or abbreviations that people use. But then Spacey is one that I mentioned. It's a really industrial sized version. So if you really want to do this in production, I would suggest looking at doing something like Spacey over NLTK. But we'll start by using NLTK and just a simple word counter with collections. So maybe we can start out by finding out how many times a word occurs in the whole corpus, so in this whole book, right? Or how many documents a word occurs in. So I'm going to start with just this one book. And so if I start with this, the first 100 characters, you can see it starts out as the one is master, the other is man, Mr. Phileas Fogg lived. And so what I'm going to do is I'm going to start with NLTK and I'm going to tokenize. So I'm going to take my corpus, right? So this is my string of all the characters in my document, in my book, my ebook. And I'm going to apply this function word tokenize. And if I get a Unicode error, I'll throw it, right? Because I don't really want to deal with those. And so when I do this, I get 75,000 total words and 7,400 unique tokens. In other words, 7,400 unique tokens. And if I start to look at these tokens at the beginning, you can see, well, I've got the one master, comma, the, well, wait a minute. That's interesting. We'll come back to that. I'm going to take a brief aside because my background's in physics and math, and so I think about these things. Years ago, a linguist, George Ziff, noted that in any big text, the nth most frequent word appears with a frequency of about 1/n of the most frequent word, and so it's called Ziff's law. It's a scale-free network sort of thing, if you want to think about it that way. And so if we plot the frequency of words, the most common first on a log-log plot, they should come up as a straight line, if that's true. So I wrote a little function to take in our term frequency. If we create it as this counter, parse it, and then plot the actual versus the projected. And so if we look in our case, and I do that, so I'll just do it live just to, oops. And so the predicted is in orange, and then what we actually got was blue. So that it lines up fairly well. So that's good. That's reassuring. It's always good to do these checks on yourself, right? As you're building out a framework, that these things that are self-consistent should be that way. And if we look at the top 20 most common words, you see that comma occurred 5,900 times, and the occurred 4,100 times. So remember, I mentioned that stop word thing, but you also notice, wait a minute, there's also a lot of these tokens aren't even words. There's punctuation in there, or they're simple and uninformative, things like at and not and with. You have the there capitalized, the not capitalized. So we need to get rid of these stop words and punctuation marks. We need to deal with case and sensitivity. So we're going to lowercase everything and reassess. And this time we're going to split it into sentences first. Because that helps deal with that punctuation piece as well as some of that the period. So that's what I'm going to do. So I'm going to import, instead of word tokenization, I'm going to import sentence tokenization from NLTK, and I'm going to import strings so I can get my my string. So if I do it by sentences first, then I get 3,600 sentences, and then from all of my sentences, I'm going to get the words based on the sentences that occur in word tokenize. So this is just sort of a logical thing. If you think about it, you're going to break the book. So we've constructed the book and just created it as a bunch of strings. We're going to split it into sentences, so that helps deal with some of the punctuation. We know that we'll split it there. And then for each sentence, we'll split it into words. And I'm going to filter out, that's what this function here does, anything that's not part of the string's punctuation. So if you remember before, we had I think 75,000 and 7,500 unique. So we've reduced that by 10% maybe, or a little more than that. And so now if we get at this, we still have, there's a couple punctuation marks that are still hanging around that weren't in the string token. If you look at the string punctuation is what I used. I can show you what that is. Is it not typing? Oh, shoot. Let's turn this into code. And typing one-handed is... It's okay, I'm fine. Not used to this. So you can see those are the punctuations in the standard string library. So I'm going to augment that because I don't want to get these other quotes. I want to eliminate those as well. So I'm working through this just to show you that taking something, Python is great because it's batteries included, but you got to realize what it is what those batteries are, and are they the right batteries, right? You put them in the wrong device and it's not going to work. So essentially what I did then is I imported the stop words from just the NLTK basic ones from English, and so that includes things like I, me, myself, the, and so on. And I'm going to add in some of these other punctuation marks that I found as I was looking through some of these articles or some of these books. So now I get a longer list of stop words that I'm going to remove. And so now I'm going to tokenize this and removing those stop words. And I now have 3,100 words. So I've gotten rid of a lot, like over half of them I've thrown away. But the unique tokens hasn't gone down nearly as much. So my space, remember the number of unique tokens is going to be my vector space. So it hasn't gone down nearly as much, but what I've done is I've collapsed things and gotten hopefully to more informative things. And so now the most common thing is fog. Passapartout is one of the characters in this book. Phileas is another character. And so you see those things are rising to the top now, which is good. That's a good sign because we know that those are important things in this book. I want to point out, though, that some of these unique tokens, I put that in emphasis because it's not really true, really mean the same thing or almost the same thing. Replied versus reply versus replying, hour and hours. Do we care? I mean, depending on your application, you may or may not care. And so, again, to try to reduce the dimensionality of the space, we can look at that and we can say, well, if I look at hour versus hours, in this book, hours occurs 90 times, hour occurs 55 times. And one way to get rid of those is to do stemming. So you could also do lemmatization. I can talk a little bit about the difference between those, but I'm going to use a stemmer here. And so stemming is rule-based, and it really works well for plurals. And so if I load the stemmer from NLTK, it reduces hour and hours to hour and all those other relying ones to that. So I'm going to apply that. And now when I do that, I get 3,100 or 31,000 words, and I've reduced my unique tokens now by about a third. So, and we can get to our word count in here. So now what I'm going to do is I'm going to wrap all of that into a single function. So I kind of did this step by step to show you the differences, right? Because it's, you want to build up, you want to understand what you're doing. And so, so my function now is I call it NLTK Tokenize. And so what I do, I pass in a string of text. I pass in stop words, but I have a default. I pass in a stemmer, and I have a default. And I have a flag to ignore stop words or not. And so I shouldn't have it for that, but that's okay. So I take it and I use the sentence tokenizer from NLTK and the word tokenizer to get my tokens. I remove my set of punctuations. I lowercase everything, and then I remove additional stop words, which included some of those oddball punctuation marks. And then I apply the stemmer if that exists, and then I return that. So if I do this now, I can do this for each chapter in my book. I'm dealing with Around the World in 80 Days, and it runs pretty quickly. And I wrote a little helper function just to, again, check on how things, so I'm getting my stats. So by chapter, So I just did a histogram to say, well, how many chapters have and how many unique words, and so this should correlate with the number of, I keep bumping things, sorry. This should correlate with the length of the chapter, if you want to think about it that way. But and so you can kind of see that when I just get the chapter stats. This is the number of words, and that's the number of stats. All right, I just got to keep my finger off of the trackpad. I think that's the moral of the story. So this book had 37 chapters, sorry, 0 indexed. And so we can go there, and the question then becomes, now we've done this pre-processing, right? So we haven't really done much, we've just been pre-processing. Can we distinguish or cluster the chapters based upon the words on them? And so that's one of the first tests of like, well, what can we do? So what I'm going to do is I'm going to say, well, let's look at all of my chapters, right, and look at the most common words in each chapter and just concatenate those. So when I start to do that, so this is now by chapter, you can see the top 5 words in each chapter, and there's a lot of similarity, right? Fog, Phileas, Parsipot, fog comes up there in a lot. Looking at a bunch of lists is about as fun as looking at a bunch of Excel spreadsheets. But we can start to then, I'm gonna skip over a little bit of this code to do this, but what I'm gonna do is I'm gonna plot these. So I'm gonna look at, for each, well, I should say what I'm doing, sorry. So I'm gonna concatenate all of those, create a set of all of the top words and all the top 5 from all of the chapters. So it comes out to be 70 words, just to give a baseline of an initial take of like, what are the important words there, right? So, so I took the top 5 words in each chapter and concatenated them and created a unique set of that, and that's where there were 70 words in this case. Nothing special about that, just a way to do it, to think about it in a sense. And so what I did here was to say, well, let me look at each of those 70 words and see where they come up in different chapters. So for example, in chapter 1, this word, and this word come up a lot, right? Club, row, Saville, fog, and Phileas. So I think fog is probably back here because it's coming up in multiple ones. And so these are just different chapters, chapter 6, chapter 9, chapter 31. So I just kind of colored them, coded differently. But it's a way of saying, the thing I like about this sort of representation is you could think about this from a almost a fingerprinting mechanism of saying, well, if we did this, we could try to compare and see how things look. And you could think about that as an application for, comparing for plagiarism or something like that. You could run things through and say, oh wait, these words are all showing up the same frequency, right? There's something going on here, right? And you would put some sort of threshold in. So we're not going to do that because we're going to try to do something else. So if we really want to do this more seriously, we probably want to deal with the fact that all we did was we counted the frequency of words, and we don't understand really how important those words are relative to the sense of how often they occur in the document and otherwise. So this is where this wonderful expression TF-IDF comes in. So TF-IDF stands for term frequency inverse document frequency. So it's a good way of overcoming concerns about overcounting or overweighting certain words in the corpus. So just because fog is present in all these chapters and all the time, is it really that important of a word in the corpus? Particularly when you start to look at, where I'm going with this is I'm going to look at this book compared to other books, right? And so how do we know, what they're about, right? How do we get a sense of what they might be about? And so if we define T as a term, D as a document, lower d, big D is a set of all documents, then the general equation is this, that it's a function, TF-IDF is a function of the term frequency and the inverse document frequency. Very simple, right? And the idea is, how do we get at how often a word occurs? So term frequency is what that's all about. It's just saying, how often does a word occur in the document, right? So it's just a number of times. And so the most frequently occurring words give some insight onto what the content's about. But if the documents you're comparing are of different lengths, you need to adjust this. And so this raw count, you can deal it by inverse document frequency. So you look across. So one way to think about this is in terms of the chapters. If we're going to look at comparing one chapter to another, we could say if we want to see if there's a word all the way through in every chapter, it's less informative, right? So we would penalize it because it occurs very often in all of the chapters. Likewise, if we were going to look at multiple books, we'd see penalize it a word like desire or friend or something like that may not be as informative, but it's present in all of those. So that's where this comes in. So again, we go back to scikit-learn just because there's a nice interface and they have TF-IDF vectorizer. Same thing I did before. So now I'm going to rejoin each token into each chapter. I'm going to fit the chapter corpus for this book. I'm going to create a couple helper functions to cluster based on the TF-IDF. And this next function is to then extract the term functions just so I can make sense of some of this, and then plot a single cluster. So I just have a couple functions. I'll skip through those. I should say, I don't want to skip through this too quickly, but what I've done is I've created a mechanism to say, well, I'm going to vectorize things, right? I'm going to score it, and so then this is going to cycle through a series of cluster sizes, because whenever you cluster, you have to determine what size cluster, how many clusters to cluster it into. Do you do one cluster? Do you do 15? Do you do 30? And so one way to do that is to have a metric to assess that. And so that's what this graph is showing, is that as I increase from having 2 clusters to, I think I went up to 19 or 20 in this case, the maximum cluster score is when I have 11. So I'm just going to choose that as my number of clusters. So again, a way of trying to get a handle on that question of how many clusters to use. And so if I do that, and I look at my chapters, and I've clustered them now into 11 clusters, cluster number or cluster ID 8, there are 5 chapters in that, and it kind of tapers off. Okay, so all I've done is I've taken each of the chapters, I've vectorized them, I've used TF-IDF, and now I can cluster them into these different different clusters, groups, and I can look at the terms in each of these clusters. So if I look at cluster ID 1, I got some of these terms like Mongolia and Suez and Fix that are relatively important. So this is just a weighting of that, versus if I look at this one's actually, Francis is really large in that cluster. So let me keep going here as I'm quickly burning my time, because what I want to do is compare this document to another document. So that was all intra-document. And so I'm going to go back to Project Gutenberg, right? So I have a little function to either read from a local file or download from the internet. And I decided to get a few more books. So I got Jules Verne, Around the World in 80 Days, which we already had. Jules Verne, 20,000 Leagues Under the Sea. Jane Austen, Pride and Prejudice. Jane Austen, Emma. Sherlock Holmes, the original, Return of Sherlock Holmes by Arthur Conan Doyle, and then Sherlock Holmes, the original. And so this was my my training set, and then I went out and got a few more. I got Journey to the Center of the Earth by Jules Verne, Sense and Sensibility by Jane Austen, and then Hound of the Baskervilles by by Arthur Conan Doyle. So again, the question becomes, do these authors, write in a certain way that you could use a machine to try to tell you that this book was by this author, right? That's kind of the problem statement here. So I'm going to go through all the same sort of pre-processing. I'm going to tokenize, remove stop words, remove punctuation, and stem. And so I do this for each. So I have this class of chapters, but I do this by chapter, by book, process all this through. So now I have, this is 225 different chapters, right? So they've all been concatenated together, and they're present in 6 books. So I can look at, by book or by chapter. That's all this helper function up here was doing, was splitting it all out. So let's go to this. So I've got a corpus that's 1 row for each chapter and a corpus that's 1 row for each book. So let's start with the second one and see if we can see differences between these. So I created a data frame of these and start with the TF-IDF vectorizer, which is I did. So I do this fit transform, right, and get my feature names. And so I have now, if I do this across the whole corpus, I now have 14,935 features, right, unique tokens. And here's at the end of it. You know, we always start with the beginning, so I thought I'd start with the end. Those are the last features there. And so the dimension of our document to word matrix now is 6 by 14,935. And so I can take a look at that and just see what, you know, the dot product of that is. And so you would see the diagonals. And just from that simple dot product, you can see, well, we're not doing as well for the Jules Verne. I think that I got to think about my order here. Yeah, Jules Verne are the first two. And then here's the Jane Austen books. And then the last two are the Arthur Conan Doyle, which is actually a little bit satisfying because we know that the main characters in both those books are the same people. So it makes sense that those might be more similar, right? Versus doing it from, you know, Jules Verne, who wrote, you know, in a certain style, but his characters were very different in 80 Days versus in 20,000 Leagues Under the Sea. So, so if we try this at the chapter level and we start to do this vector, you can do the same sort of thing. And to guide your eyes, I drew boxes around each book, and you can see that at least within each book, there's more self-similarity, right? So definitely there's good self-similarity there. There's a little bit of shading here to show that Jane Austen's books might be more similar, and again, the Conan Doyle. So cool, we can kind of see that chapters of contiguous books are more self-similar. We may not see as many similarities within an author, but what else can we do? And so this is where this gets to some of the really cool stuff. We're gonna run out of some time. I've got it in here. I'm gonna say topic modeling. So topic modeling is a mechanism by which we're projecting now. We're trying to reduce the time or the dimensionality of the space, right? And this is just a mechanism to do that. And so it works by identifying the informative co-location and breaking it down. So I'm gonna skip over the math here because you guys wanna see the results, right? And so I'm going to import this TF-IDF. I'm going to go by the whole book. And I just chose 2,000 as my dimension space. So we're going to dimension reduce it that way. And so I'm going to apply NMF, which is one algorithm, and LDA, which is another one. And I'm going to display the topics from these. So if I look at these two models, topic 0 comes out with things like Holmes, Watson, Sherlock, Lestrade. Topic 1 has Elizabeth, Harriet, Jane. Topic 2 has Ned, Canadian. That's from the one model. The other model kind of flips the order of things a little bit. Still, it looks like there's some things coming up. It looks like it merges some of the Jane Austen stuff with the Sherlock Holmes stuff. So, so I have a helper function to try to show these. I'm going to plot some of these words. So let me just skip down to it. So this is the book ID, right? Versus the topic ID. And so you can see that at least for a couple of the books, right, those come together, right? And these two, so sorry, saying book 0 and 1, right, they don't necessarily come together as much, but 2 and 3, they really co-locate in the same topic, at least by this general sense. And so when we look at that, we see that, oh, what's happening is that we're not getting 80 days being picked up by these topics. It kind of gets spread out among the other topic space, right? So you've projected it into this topic space where the 2 Sherlock Holmes books are together, the 2 Jane Austen are together, but not the others. And again, similar sort of thing for the other model. It's just a little bit different distribution. And we can look at what words are present in there. And we can see that like topic 0 from the LDA is Ned. Again, these bar graphs are kind of useful. Let me jump down because we showed this thing about visualization. So it's not so surprising that 3 topics didn't exactly map. Again, just like determining the number of clusters, the catch with topic modeling is you have to determine the number of topics. And so it's kind of a trial and error sort of thing. But I do want to show one last thing of when I did more topics. We can get to this visualization called PyLDA Viz. So if you haven't seen this, it's pretty cool. It works with GenSim, which is another text processing library, which I can talk to you guys more about offline. But this is the interface for it. So what it's doing is, so this is with the 3 different topics. And so on the right, it's giving the relevant, the 30 most salient terms, right? And you've got to an interactive widget here so you can adjust this metric a little bit. But what this is saying is that how frequent are these happening overall in our whole corpus, right? So you can see where some of these words are. Holmes is up there quite a bit, Mrs., Elizabeth, so forth. And as you select a certain topic, you can see how much more proportional they are in that topic relative to the background. And so it's a really nice way to, toggle through and see, like, as I change my topic, you can see which words are really coming to the top. So if we get to topic 3, we're getting into things that deal with around the world in 80 days versus topic 2, which has more to do with, that's 20,000 Leagues Under the Sea. And then this is Sherlock Holmes plus the Austen books as they're thrown together in this particular model, right? So I've exhausted my time. I've got other fun graphs. Oh, I'll show you one more graph to talk about. So if I apply this, I said I was going to load this in. So I loaded in Journey to the Center of the Earth, Sense and Sensibility, and the Hound in the Baskervilles. So if I do that and I apply to this test set, and I do a color correlation, I can get that. Not so bad that the Verne books map to this, the Austen books are here, and then the Doyle books correlate there. So it's not a bad model for just doing all this. And I should stop there, because the only other thing I had was to show characters through time. So, but I've exhausted my time, so thank you.
All right. So I think we had a couple questions on the
Okay, so
board
let's
up
look at
here.
this. Let's see. Let me try to answer these. Let's see. So I did the one about insurance. So a unified canonical NLP program. That's a great question. I think there's been a lot of movement towards using deep learning towards some of this, and so I think that's where there's been some strides. And I didn't present anything here to do that. I know that. Yeah, I'm not sure about a unified. I guess I don't know quite how to answer that question. So maybe I can talk to you, Scott, later. Rules of thumbs about the size of data needed. That's a good question. So I think the rules of thumb apply more to how you tokenize things in a way, right? So you've got this trade-off with your amount of space and the computing power, because I mean the NMF is a matrix problem, right? It's a matrix inversion thing. So as you get larger space, then you're not getting there. And as you go to, I just showed things with 1 grams, but as you can think about this, as you go to larger and larger Engrams, then your space can grow quite a bit, right? You have a lot more things to consider. And so how do you do that at scale? And so I think GenSim is a great library for dealing with that. I didn't show much about GenSim here, but that, because it's a little harder to get your head around what it's doing. So I felt like the NLTK and the scikit-learn approach shows you a little bit more what's doing. And I think it's really about trying it out a little bit to get that. There's a good slide about the rules of thumb. I'll have to look that up and maybe post it on there if I can find that. So, all right, thank you.